Have you ever looked up at the night sky and felt like there was something more, something hidden just beyond what your eyes can see? What if the universe isn't just a random collection of stars and galaxies, but a carefully woven tapestry filled with patterns so precise they seem almost intentional? From the spiraling arms of galaxies that mirror the curves of seashells to the way light echoes across the cosmos in perfect mathematical harmony, there are clues everywhere, whispers of a deeper order. These aren't just coincidences, they're puzzles waiting to be solved, and they might just hold the key to understanding the very fabric of reality. Think about the last time you noticed a pattern in nature, the way tree branches split, the swirl of a hurricane, even the rhythm of your own heartbeat. Now imagine that same order repeating itself on the grandest scale imaginable, from the smallest atoms to the vastest stretches of space. Scientists have catalogued dozens of these eerie symmetries, and each one raises more questions than answers. Why do galaxies arrange themselves in geometric formations? How does the cosmic microwave background, the faint afterglow of the Big Bang, carry such uniform imperfections, almost like a code etched into the universe itself? These aren't just curiosities, they're potential breadcrumbs leading us toward a truth far stranger than fiction. This journey isn't just about observing the universe, it's about rethinking what it means to exist within it. What if these patterns are more than just accidents of physics? What if they're signatures of something larger, a hidden architecture binding everything together? Over the next 36 revelations, we'll explore everything from the golden ratio's haunting presence in black holes to the mysterious voids in space where matter seems to avoid clustering, as if guided by an unseen hand. By the end, you might not just see the cosmos differently, you might wonder if it's been trying to tell us something all along. So let's begin. The universe is waiting. One of the most mesmerizing examples of cosmic order is the way spiral galaxies unfold their arms with near-perfect mathematical precision. Look at the Milky Way or the Whirlpool Galaxy, and you'll notice their swirling structures aren't chaotic. They follow the golden ratio, the same exact pattern seen in sunflowers, hurricanes, and even the curl of a crashing ocean wave. This isn't just a visual coincidence. The Fibonacci sequence, where each number is the sum of the two before it, appears to govern the growth of these galactic arms, spacing them at angles that create an eerie harmony between math and nature. Why does this happen? Some researchers argue it's simply the most efficient way for matter to organize under gravity's pull, like water spiraling down a drain. But others see something deeper, a hint that the universe might favor certain shapes, almost as if it's following an invisible recipe. Dark matter, the mysterious substance that makes up most of the cosmos's mass, could be subtly sculpting these spirals into their precise forms. Or perhaps quantum fluctuations in the early universe imprinted this pattern like a cosmic fingerprint, guiding galaxies to grow in these elegant curves. The debate touches on a much bigger question. Is math something humans created to describe the world, or does it exist independently, waiting to be uncovered? When we see the golden ratio in galaxies, seashells, and even DNA, it's hard to shake the feeling that we're glimpsing a hidden language, one the universe has been speaking since the beginning of time. If that's true, then every spiral in the night sky isn't just a beautiful accident. It might be a clue pointing us toward a truth far grander than we've ever imagined. But if galactic spirals suggest a hidden mathematical order, quantum entanglement shatters our conventional understanding of reality entirely. Picture two particles born from the same event, maybe photons created in a lab or electrons spinning around an atom. Separate them by the width of a galaxy, and here's the astonishing part. Change one, and the other instantly responds as if they're still touching. No signal passes between them. No force travels the distance, they just know. Einstein famously dismissed this as spooky action at a distance, convinced it revealed a flaw in quantum theory. Yet experiment after experiment, from labs on Earth to satellites in orbit, has proven entanglement is real. The universe, it seems, doesn't play by the rules we thought it did. What makes this so revolutionary isn't just the violation of classical physics. It's the implication that space itself might be a kind of illusion. Think of it like two ends of a stretched rubber band. Tug one side and the other moves immediately, not because something traveled between them, but because they're fundamentally part of the same system. Quantum entanglement suggests the cosmos might work the same way, that what we perceive as vast, empty distances could be superficial, like stitches holding together a far deeper fabric. Some theorists even propose that entanglement threads through the entire universe, weaving particles into a web of instant connection that defies time and space. And here's where it gets stranger. If entangled particles communicate faster than light, as experiments imply, then causality, the idea that cause must always precede effect, starts to unravel. Could this be why black holes, those cosmic vacuum cleaners, seem to preserve information in ways that defy physics? Or why certain particles appear to remember their entangled partners across billions of years? The more we study these phenomena, the more the universe feels less like a collection of isolated objects and more like a single, pulsating network. Entanglement might not just be a quirk of quantum mechanics. It could be the first clue that separation itself is an illusion, and that everything from the dust on your bookshelf to the farthest quasar is whispering to each other in a language we're only beginning to decode. Now picture zooming out from those entangled particles, pulling back until entire galaxies shrink to specks of light, and suddenly the universe reveals its grand design. What was once thought to be random chaos resolves into an intricate cosmic web, a sprawling network of galaxies clustered along shimmering filaments, with vast voids stretching between them like the empty spaces in a spider's silk. This isn't just structure, it's a fractal, a pattern that repeats itself from the tiniest quantum foam to the largest superclusters, as if the universe is echoing the same blueprint across every scale. What's astonishing is how closely this cosmic web mirrors other networks in nature. The branching veins of a leaf, the firing neurons in your brain, even the tangled roots of a forest, all share that same web-like architecture. Scientists call it scale invariance, the idea that certain shapes persist no matter how far you zoom in or out. But here's the twist: this fractal universe might be more than just a pretty coincidence. Some theorists suggest it's evidence of a holographic principle, where our three-dimensional reality is actually a projection of information encoded on a two-dimensional surface at the edge of the cosmos. Imagine the universe as a movie screen, and everything we see, stars, planets, even us, is just shadows cast by something far stranger happening behind the scenes. The implications are dizzying. If the cosmic web is a fractal hologram, then the voids between galaxies aren't empty, they're part of the code. The way matter clumps along filaments might not be random but dictated by deeper, unseen rules, like pixels arranging themselves on a screen. Even more provocative, this could mean the universe has a built-in resolution limit, a smallest possible pixel of reality beyond which nothing can be divided. It's as if existence itself has a grain, a texture we're only beginning to trace. And then there's the haunting question: who or what wrote the pattern? Is the cosmic web simply gravity's handiwork over billions of years, or does it reflect something more profound, a signature woven into the fabric of space-time? When we look up at the night sky, we might not just be seeing stars. We might be staring at the universe's operating system, a hidden framework holding everything together, one thread at a time. Take a deep breath. That oxygen filling your lungs exists because of an almost impossible balancing act, one where the fundamental forces of the universe align with uncanny precision. If gravity were just a fraction stronger, stars would collapse into black holes before life could ever emerge. If the electromagnetic force were slightly weaker, atoms wouldn't bond, and molecules, like the ones that make up your DNA, would never form. Even the tiniest tweak to the strength of the strong nuclear force, which glues atomic nuclei together, would leave the cosmos either barren of elements or drowning in a sea of hydrogen. The odds of all these constants lining up perfectly, astronomically low, yet here we are in a universe that seems tailored for existence. This isn't just theoretical. Consider carbon, the backbone of life as we know it. For carbon to form inside stars, a very specific resonance level had to exist in the carbon-12 nucleus, a rare quantum fluke predicted by physicist Fred Hoyle. Without this exact energy state, stars couldn't forge the heavy elements that build planets and people. Hoyle himself, once a staunch atheist, admitted the discovery shook him, calling it evidence of a superintellect tinkering with physics. So what explains this fine-tuning? One possibility is the multiverse, an endless sea of universes, each with random physical constants. In most, conditions are too hostile for life. But in a rare few, like ours, the numbers align just right. It's like rolling a trillion-sided die and landing on the one combination that allows galaxies, planets, and consciousness to emerge. Another, more provocative idea, that these constants aren't accidents at all. Some researchers point to the mathematical elegance of the universe, where fundamental forces interlock like gears in a cosmic machine, suggesting a deeper order, or even intention behind the numbers. But here's the twist: fine-tuning might not stop at physics. Even the shape of space-time appears optimized for discovery. If the universe expanded too quickly after the Big Bang, matter would have spread too thin for gravity to pull galaxies together. Too slow, and everything would have collapsed back into a singularity. Instead, we exist in the narrowest of sweet spots, where the cosmos unfolds just fast enough to create structure, but not so fast that it tears itself apart. It's as if the universe wanted to be explored, to give rise to minds capable of unraveling its mysteries, whether by chance, necessity, or something beyond our current understanding. The precision of these constants doesn't just make life possible. It makes the universe feel strangely alive. Among the countless oddities in the cosmos, few are as baffling as quasars, those brilliant beacons powered by supermassive black holes, whose light reaches us from the edge of time. But here's the real shocker: when scientists studied the polarization of light from these distant objects, they found something that defies all expectations. Quasars separated by billions of light years, with no conceivable way to interact, somehow emit light waves vibrating in the same precise direction. It's as if an invisible hand reached across the universe and aligned them like compass needles pointing north. This isn't just a statistical fluke. The odds of this alignment happening by chance are astronomically slim, like flipping a coin 1,000,000 times and landing heads every single time. So what's really going on? One possibility is that these quasars are tethered by something we can't see, perhaps vast cosmic filaments, strands of dark matter weaving through the void, gently nudging the light into harmony. Or maybe space-time itself has a hidden grain, a preferred direction imprinted during the universe's birth, like the subtle ridges on a vinyl record guiding the needle. But the most mind-bending explanation, that this alignment hints at a symmetry deeper than anything in our current physics. Think of it like this: when you look at a snowflake, its six-fold symmetry reveals the underlying rules of how water molecules bond. In the same way, quasars might be tracing the contours of a fundamental structure, one that operates on scales so vast we're only seeing the faintest shadow of it. Some theorists even suggest this could be evidence of a pre-Big Bang phase, where the universe's initial conditions left behind a ghostly imprint, like fingerprints on a cosmic window. And here's where it gets truly wild. If this alignment isn't random, then the very fabric of reality might have a preferred axis, a cosmic north that orients everything from quasars to quantum particles. That would upend one of physics' most cherished principles, isotropy, the idea that the universe looks the same in all directions. Suddenly, the night sky isn't just a scatter of stars, it's a map with hidden coordinates waiting to be decoded. Whether it's dark matter, undiscovered physics, or something beyond our imagination, one thing's clear: the universe is whispering in a language we're only beginning to hear. And every aligned quasar is another letter in its cryptic message. If galaxies were cities, dark matter would be the hidden scaffolding holding them together. An invisible framework we can't see, touch, or directly detect, yet without it, the entire cosmic metropolis would collapse. This mysterious substance doesn't emit light, absorb it, or interact with ordinary matter in any way except through gravity. But here's what's truly bizarre. When scientists map its presence by observing how it bends light or tugs on stars, dark matter doesn't spread out randomly. Instead, it forms vast, intricate filaments, a cosmic spiderweb stretching across billions of light years, with galaxies clinging to its threads like dewdrops on silk. Why does this matter? Because this web isn't just structure, it's behavior. Dark matter clusters in ways that defy what we know about gravity. Take the Bullet Cluster, where two galaxies collided, and their dark matter sailed right through the chaos, leaving their visible stars lagging behind. It's as if dark matter exists in a parallel reality, barely noticing the matter we see. Some theorists speculate this could mean dark matter isn't just a single particle, but an entire hidden sector of physics, a kingdom of particles and forces operating alongside ours, forever out of reach. Even stranger, the way dark matter's web mirrors quantum entanglement's invisible connections. Just as entangled particles respond instantaneously across vast distances, dark matter's filaments seem to know how to arrange themselves in eerily precise patterns. Could there be a link between these phenomena, a deeper layer of reality where gravity and quantum weirdness intertwine? Some bold hypotheses suggest dark matter might not even be matter at all, but a shadow cast by vibrations in higher dimensions, like ripples on a pond we can't see. And then there's the elephant in the room. What if dark matter isn't the anomaly? What if we're the outliers and the universe is fundamentally built from this invisible fabric, with ordinary matter just a fleeting afterthought? The more we study its gravitational fingerprints, the way it sculpts galaxy rotations, bends spacetime into lenses, even dictates the universe's ultimate fate, the more it feels like we're deciphering the universe's hidden blueprint. Dark matter isn't just a missing piece of the puzzle. It might be the table the puzzle sits on, the quiet architect of everything we perceive. The cosmic microwave background is like a snapshot of the universe's infancy, a faint glow from when the cosmos was just 380,000 years old, stretched across the sky in every direction. But here's what stops physicists in their tracks. This ancient light is almost perfectly uniform, with temperature fluctuations so tiny they're measured in thousandths of a percent. Picture baking a cake where every single crumb, no matter where you slice it, is identical down to the molecular level. That's the level of precision we're talking about, a homogeneity so exact it defies intuition. How could regions of the early universe, separated by distances light hadn't even had time to cross, reach such equilibrium? Standard physics says heat should spread unevenly, leaving patches warmer or cooler as energy ebbs and flows. Yet the cosmic microwave background shows no such imbalance. Inflation theory, the idea that the universe underwent a fleeting, exponential expansion in its first split second, offers one explanation. By stretching space itself faster than light could travel, inflation could have smoothed out irregularities, ironing the cosmos into uniformity like a cosmic steamroller. But some researchers aren't convinced. The math works, yes, but inflation feels almost too convenient, like inventing a new law of physics just to solve this one puzzle. Alternative theories are bubbling up. Maybe the early universe wasn't a chaotic soup but a structured fluid, with quantum entanglement linking distant regions before space even finished inflating. Or perhaps what we're seeing is evidence of a cyclic universe, where the Big Bang wasn't a beginning but a rebirth from a previous cosmic phase, imprinting order like a fingerprint pressed into wet clay. Then there's the axis of evil, an unsettling pattern in the cosmic microwave background where temperature fluctuations appear slightly aligned along a particular plane, as if the universe has a subtle tilt. This anomaly resists both inflation and randomness, hinting that our cosmic snapshot might be cropped from a larger, stranger picture. Could this axis be a relic of higher dimensional physics, like shadows cast by structures we can't perceive? Or is it a statistical mirage, a trick of perspective wheel decoded with better data? The deeper we probe, the more the cosmic microwave background feels less like a relic and more like a cipher, a message from the universe's first moments, written in a code we're still learning to read. Its uniformity might not just be a quirk of expansion. It could be evidence of a deeper connectivity, a hidden architecture that bound everything together before time even had meaning. And if that's true, then the afterglow of creation isn't just light. It's a mirror reflecting a universe far more intertwined than we ever imagined. Imagine the universe as a cosmic heartbeat expanding, contracting, and expanding again in an endless rhythm where each breath lasts billions of years. This isn't science fiction. Some of the most compelling models in theoretical physics suggest our universe might not be the first or the last in an infinite series of cosmic cycles. The evidence, subtle fingerprints hidden in the way galaxies cluster and how radiation lingers in the void, as if space itself remembers its past lives. Take the large-scale structure of the cosmos. When astronomers map the distribution of galaxies, they don't find randomness. Instead, galaxies arrange themselves in vast, repeating superstructures, walls, and filaments that echo across billions of light years. These patterns shouldn't persist if the universe had a single, linear beginning. But if space has cycled through countless expansions and collapses, each iteration could have left behind gravitational imprints, like waves fossilized in stone, guiding matter to clump in eerily familiar ways. Then there's the cosmic microwave background. That faint afterglow of the Big Bang carries tiny temperature fluctuations, a relic of quantum ripples from the universe's infancy. But some of these fluctuations appear too uniform, too perfect, as if they're not just random noise but echoes of a previous cycle's final moments. Think of it like a pendulum swinging back and forth. Each time it reaches its peak, it leaves a trace of its momentum, shaping the next swing. If the universe follows a similar rhythm, those ripples might be the cosmic equivalent of a pendulum's ghostly afterimage. The math behind cyclic cosmology is equally mesmerizing. In these models, the universe doesn't end in a heat death or a big crunch. Instead, it reaches a maximum expansion, then rebounds, a process driven by dark energy transforming into matter, resetting the clock for a new cycle. Each rebirth would carry forward faint remnants of the last, perhaps twisted magnetic fields threading through galaxies, or black holes from a prior universe lingering like cosmic elders. But here's the twist: if cycles are real, time itself might be an illusion. In a truly eternal loop, beginnings and endings blur. Our Big Bang wouldn't be a singular event, just one note in an infinite symphony, with each universe inheriting a whisper of the one before. That raises a haunting question. If the cosmos forgets nothing, are we, right now, living in the shadow of a forgotten iteration? The answer might be written in the voids between stars, waiting for us to listen. Pulsars are the universe's most precise timekeepers, cosmic lighthouses spinning at dizzying speeds, their beams of radio waves sweeping past Earth with a regularity that rivals atomic clocks. These collapsed cores of dead stars, no larger than a city yet denser than the sun, should be isolated actors, each dancing to its own rhythm. But something strange happens when scientists listen closely. Some pulsars, separated by thousands of light years with no conceivable way to communicate, somehow fall into sync, their pulses aligning as if guided by an invisible conductor. Take PSRB 1937+21, one of the fastest known pulsars, spinning over 700 times per second. Its ticks are so precise, they're used to test Einstein's theory of relativity. Yet when researchers compared its rhythm with other millisecond pulsars, they found eerie correlations, tiny deviations that mirrored each other across vast distances. It's like discovering two metronomes in different countries ticking in perfect unison, despite never being wound or set to the same tempo. So what's really happening? One possibility is that these pulsars are entangled by gravitational waves, ripples in space-time from cataclysmic events like colliding black holes. These waves could subtly nudge the star's rotations, syncing them like pendulums on a shared rope. Another theory points to dark matter. If certain types of dark particles interact weakly with neutron stars, they might form a diffuse medium that transmits timing signals, a cosmic network humming just beneath our perception. But the most tantalizing idea, that pulsars aren't just keeping time, they're responding to something deeper. Think of them as tuning forks vibrating in harmony with the fabric of space-time itself. Some physicists speculate that the universe has a fundamental frequency, a background hum left over from the Big Bang, and pulsars are somehow attuned to it. If true, their synchronicity isn't a glitch, it's a clue. Every matched pulse might be a flicker of a larger pattern, a rhythm woven into the structure of reality. And here's where it gets even stranger. If pulsars are synchronized by a universal force or field, it could mean that time itself isn't as local as we think. Just as quantum entanglement suggests space might be an illusion, pulsar synchronicity hints that time, at some level, might be more interconnected than we ever imagined. The universe isn't just ticking away, it's conducting a symphony, and these dead stars are its most loyal musicians. Whether it's gravity, dark matter, or something beyond our current physics, one thing's clear: the cosmos has a beat, and we're only just beginning to hear it. Black holes aren't just cosmic vacuum cleaners, they're laboratories of the most extreme physics, where the known laws of reality twist into something stranger. Take their entropy, for example. In everyday life, entropy measures disorder. Think of a melted ice cube, its molecules scattered and chaotic. But a black hole's entropy isn't about particles. It's tied to the surface area of its event horizon, the point of no return. The larger the horizon, the more entropy the black hole holds. This bizarre connection, discovered by physicist Jacob Bekenstein, hinted at something revolutionary. Black holes don't just swallow information. They store it like a cosmic hard drive with data etched onto their boundaries. Then there's Hawking radiation, the faint glow that black holes emit, proving they're not entirely black. Stephen Hawking showed that quantum fluctuations near the event horizon allow particles to escape, slowly evaporating the black hole over eons. Here's the twist: This radiation carries a temperature, meaning black holes obey thermodynamic laws, just like a steaming cup of coffee. But how can an object defined by gravity alone behave like a thermal system? The answer might lie in the holographic principle, the idea that all the information inside a black hole is encoded on its two-dimensional surface, like a movie projected onto a screen. This revelation shakes the foundations of physics. If a black hole's three-dimensional interior can be fully described by data on its two-dimensional edge, could the entire universe work the same way? Some theorists argue yes, that reality itself might be a hologram, with the cosmos functioning like a vast, interconnected code. Black holes then aren't just oddities. They could be keys to unifying gravity and quantum mechanics, two frameworks that have resisted reconciliation for a century. But the strangest part: black holes might not just store information, they could transform it. When matter falls in, it's stretched into strings of energy, a process called spaghettification. Yet the holographic principle suggests this information isn't lost. It's scrambled like a cosmic encryption and preserved on the horizon. If we could decode it, we might unlock the universe's deepest secrets, like reading the fine print on the fabric of space-time. This isn't just theoretical gymnastics. Recent experiments with quantum computers simulate black hole dynamics, and the results are uncanny. Certain quantum systems behave like microscopic black holes, displaying similar entropy and information retention. It's as if nature keeps whispering the same rules at every scale, from the tiniest particles to the darkest voids. Whether black holes are cosmic accidents or deliberate puzzles, one thing's certain: they're not in points. They're gateways to a theory of everything, to hidden dimensions, or perhaps to truths we haven't even imagined yet. The more we study them, the more they feel less like monsters and more like messengers, bridging the gap between the quantum and the cosmic in ways we're only beginning to grasp. Zoom in on an atom, any atom, and you'll find electrons whirling around a nucleus in a delicate dance of attraction and motion. Now pull back, way back, until that atom becomes a speck in a galaxy, where stars spiral around a supermassive black hole with that same hypnotic rhythm. The resemblance is uncanny. It's as if the universe hit copy and paste, scaling up the same blueprint from the infinitesimally small to the astronomically vast. This isn't just poetic symmetry, it's a pattern so precise it forces us to ask: are galaxies just giant atoms, or are atoms miniature galaxies? The parallels run deeper than you might think. In both systems, gravity, or its quantum counterpart, the electromagnetic force, keeps the smaller objects in orbit. Electrons occupy specific energy levels, like rungs on a ladder, never hovering between them. Stars, too, follow preferred orbits, clustering in galactic arms with mathematical regularity. Even the empty space is eerily similar. An atom is mostly void, with the nucleus a tiny speck at its center. A galaxy, same story. If you shrank the Milky Way down to the size of a football field, our solar system would be a grain of sand lost in that expanse. But here's where it gets provocative. This scale invariance isn't limited to atoms and galaxies. Neurons in your brain branch like cosmic webs. Lightning forks mimic the fractal veins of river deltas. Even the internet structure mirrors the universe's large-scale filaments. It's as if nature has a favorite shape, a template it reuses across dimensions, tweaking only the details. Some physicists argue this isn't accidental. They point to the holographic principle, where the universe's information might be encoded on its boundary, projecting inward like a shadow puppet show. In this view, atoms and galaxies aren't just similar, they're different resolutions of the same underlying code. Then there's the math, the equations describing orbital motion, whether an electron around a nucleus or a star around a black hole, share striking similarities. Newton's law of gravitation and Coulomb's law of electric forces both follow an inverse square rule, where strength diminishes with distance squared. Coincidence maybe, but when you add quantum mechanics to the mix, things get even weirder. Electrons don't orbit like planets, they exist as probability clouds, yet their wave functions resonate with the same harmonics seen in galactic density waves. It's as if the universe is humming the same tune, whether it's composing subatomic particles or symphonies of stars. So what does it all mean? One possibility is that we're seeing the fingerprints of a deeper, unified physics, a theory where gravity and quantum forces emerge from the same source. String theory, for instance, suggests that at unimaginably small scales, everything vibrates in higher dimensional harmonies. Alternatively, this could be evidence of a simulated universe where limited computational resources reuse the same algorithms at different scales. Or perhaps it's simpler, the universe optimizes. Just as soap bubbles form perfect spheres to minimize surface tension, maybe nature defaults to certain shapes because they're the most efficient ways to organize energy and matter. Whatever the explanation, one thing's clear: the boundary between the microscopic and the cosmic is far blurrier than we once thought. When you look at a galaxy, you might be staring at the universe's way of whispering, "This is how things are built." From the smallest quark to the largest supercluster, the same patterns echo, hinting at a hidden language, one we're only beginning to decipher. Somewhere out there, in the direction of the constellation Boötes, lies a cosmic desert so vast it defies belief, a spherical void stretching 330 million light-years across, containing almost no galaxies. Picture holding a beach ball up to the night sky. Now imagine that ball scaled up to cosmic proportions, enclosing a space where starlight barely flickers. This is the Boötes Void, one of the largest known structures in the universe, and one of the most baffling. According to standard cosmology, matter should be distributed relatively evenly across the cosmos, with only modest variations. But the Boötes Void isn't just a quiet neighborhood. It's a ghost town, a gaping hole in the cosmic web where galaxies should be thriving but instead are almost entirely absent. How does something like this form? One theory suggests it's the aftermath of an ancient collision between universes in the multiverse, like a bruise left behind when two cosmic bubbles brushed against each other. In this scenario, the void could be a scar, a region where matter was somehow pushed out or erased by forces beyond our current understanding. Another idea points to dark energy, the mysterious force accelerating the universe's expansion. If dark energy behaves in unexpected ways, it might have carved out these voids by aggressively repelling matter over billions of years, leaving behind cosmic dead zones. But here's what's truly unsettling. The Boötes Void isn't alone. Other giant voids, like the KBC Void and the Taurus Void, dot the observable universe, each challenging our models of structure formation. These aren't just empty spaces, they're too empty, as if someone took an eraser to the universe's blueprint. Some researchers speculate they could be evidence of exotic physics, like quantum tunneling on a cosmic scale, where entire regions of space underwent a phase transition in the early universe, locking them into a barren state. Or perhaps they're shadows cast by higher dimensional objects, like a four-dimensional sphere passing through our three-dimensional reality, leaving spherical voids in its wake. Then there's the eerie possibility that these voids aren't empty at all. What if they're filled with something we can't see, not dark matter, but something even stranger, like a false vacuum or a hidden sector of particles that don't interact with light? If so, these cosmic deserts might be teeming with invisible activity, a bustling metropolis of exotic physics we're only glimpsing through its absence. The Boötes Void doesn't just defy expectations, It forces us to reconsider the very nature of emptiness. Is it truly nothing, or is it a window into a deeper layer of reality where the rules we know don't apply? Every time we point our telescopes at these vast, silent regions, we're not just staring into space, we're staring into a mystery, one that might rewrite our understanding of the universe itself. When NASA Pioneer 10 and 11 spacecraft ventured beyond the asteroid belt, they carried humanity's first messages to the stars' gold plaques etched with symbols of our existence. But as they drifted farther into the void, scientists noticed something bizarre. Both probes were slowing down ever so slightly more than physics predicted. Not by much, just a fraction of a nanometer per second squared, but over decades and billions of miles, that tiny discrepancy grew into one of the most enduring mysteries in space exploration, the Pioneer Anomaly. At first, researchers assumed it was a simple engineering glitch, perhaps heat radiating unevenly from the probe's power systems, giving them an imperceptible push. But when they crunched the numbers, thermal radiation could only account for part of the deceleration. The rest defied explanation. It was as if an unseen hand were gently tugging the probes backward, a force too subtle to detect directly but too consistent to ignore. The implications sent shockwaves through physics. Could this be evidence of a fifth fundamental force, one that only manifests over vast distances? Some theorists proposed modifications to Einstein's general relativity, suggesting gravity might behave differently at the solar system's edge. Others wondered if dark matter, usually thought to clump around galaxies, might form a diffuse halo around our solar system, subtly altering the probe's trajectories. But the most radical idea, that the anomaly hints at hidden dimensions, realms beyond our four-dimensional spacetime where gravity leaks in unexpected ways, like water seeping through cracks in a dam. Then there's the eerie timing. The Pioneer Anomaly vanished as the probes crossed the threshold of about 20 astronomical units from the Sun, roughly where the influence of solar radiation weakens. Was this a clue? Some scientists speculate that the anomaly might be tied to the Sun's gravitational field, interacting with unknown physics at cosmic scales, a phenomenon we've yet to model. Others point to the cosmic microwave background, the afterglow of the Big Bang, which permeates space with a faint pressure. Could it exert just enough drag to explain the slowdown? Decades later, the mystery endures. Newer spacecraft like New Horizons don't show the same anomaly, perhaps because their designs minimize thermal effects, or maybe because the force only acts on certain trajectories. Either way, the Pioneer probe's unexplained behavior lingers like a cosmic riddle, whispering that our understanding of gravity, space, and even reality itself might be missing a crucial page. What makes the anomaly so tantalizing isn't just the unsolved math, it's the possibility that we're glimpsing the edge of known physics. Every unexplained drift, every tiny deviation, could be a breadcrumb leading to a deeper truth. The pioneers weren't just messengers, they might have been the first to brush against a hidden layer of the universe, one we're still struggling to see. And until we solve their riddle, their journey remains a haunting reminder. The farther we reach into the cosmos, the more it pushes back in ways we never expected. Galaxies don't just drift through the cosmos at random, they move in vast, coordinated rivers, flowing towards something we can't see. When astronomers mapped the motion of hundreds of galaxy clusters, they noticed something that defied all expectations. These colossal structures, each containing thousands of galaxies, were drifting in the same direction at staggering speeds over 2 million miles per hour, as if pulled by an invisible current. They called it the dark flow, and it's one of the most unsettling discoveries in modern cosmology. Think of it like leaves floating down a river. If you saw every leaf suddenly veer left, you'd assume something beneath the surface, a hidden whirlpool or a submerged landslide, was tugging them. The dark flow suggests the same thing on a cosmic scale, but here's the catch. Whatever's pulling these superclusters lies beyond the edge of the observable universe. That's right, beyond the cosmic microwave background, beyond the farthest light we can detect. Something unimaginably massive seems to be warping the fabric of space-time itself. So what could it be? One theory points to gravitational tides from a superstructure so vast it dwarfs our entire observable cosmos. Think of a mountain range so large, its foothills stretch beyond the horizon. If another universe or a region of extreme density exists just outside our cosmic bubble, its gravity might be leaking in, tugging everything toward it like a magnet. Another possibility that the dark flow is a relic of the Big Bang's asymmetry. If the universe didn't inflate perfectly evenly, certain regions might have retained momentum from that initial lopsided push, sending superclusters sliding in a preferred direction like marbles on a tilted table. But the most radical idea, that we're seeing the gravitational shadow of a parent universe. In some multiverse models, our cosmos could be one of many bubbles in a higher dimensional foam, each brushing against the others. If a neighboring bubble collided with ours long ago, the ripple might still be echoing through space, herding galaxies like cosmic sheep. The implications are staggering. If the dark flow is real, it means our universe isn't just expanding, it's being steered. And whatever's doing the steering lies so far away, its light hasn't had time to reach us in 13.8 billion years. That's not just a mystery, it's a frontier. Every galaxy cluster caught in this flow is a clue, pointing to forces and structures so vast they redefine what we thought was possible. The dark flow doesn't just challenge our models of the universe, it dares us to ask what else is out there, lurking just beyond the limits of our sight. At the heart of quantum mechanics lies one of the most mind-bending phenomena ever discovered. The simple act of looking at a particle changes its behavior. In experiments, particles like electrons exist in a blur of probabilities until measured, at which point they choose a definite state. It's as if reality waits for an observer to make up its mind. This isn't just a technical quirk, it's a fundamental puzzle that blurs the line between the physical world and consciousness itself. Take the classic double-slit experiment. When scientists fire electrons at a barrier with two slits, they create an interference pattern on the detector screen, behaving like waves. But the moment you place a measuring device to observe which slit each electron passes through, the interference vanishes. The electrons suddenly act like particles, as if aware they're being watched. This isn't limited to tiny particles. Larger molecules, even entire atoms, show the same eerie sensitivity to observation. The unsettling implication: reality might not be fixed until we interact with it. So what's really happening? One interpretation suggests that consciousness collapses the wave function, the mathematical description of quantum probabilities, forcing particles into definite states. This idea, championed by figures like physicist John von Neumann, implies that the mind isn't just observing reality, but actively participating in its creation. Another view argues that it's not consciousness per se, but any interaction with a macroscopic system that causes the collapse. Yet even this pragmatic explanation doesn't erase the strangeness. The universe appears to know when it's being measured, adjusting its behavior accordingly. Then there's the participatory universe theory, inspired by physicist John Wheeler. He proposed that we live in a cosmos where observation shapes the past as well as the present. In his delayed choice experiments, decisions made after a particle has already traveled its path seem to retroactively determine how it behaved earlier. It's like a cosmic game of 20 questions where the answers rewrite the questions themselves. If true, this would mean the universe isn't just a static stage. It's a dynamic, co-created performance where observers and the observed are inseparable. The implications ripple far beyond physics. If consciousness plays a role in shaping reality, does that mean the universe is somehow aware? Could this explain why the constants of nature are so finely tuned for life? Because observers are necessary to bring the cosmos into focus. Skeptics argue that quantum effects decohere at larger scales, preventing our thoughts from directly influencing the macro world. But others wonder if the boundary between quantum weirdness and everyday experience is more porous than we think. Perhaps the most profound takeaway isn't about particles or equations, it's about perspective. The observer effect forces us to confront the possibility that reality isn't an external, detached entity. Instead, it might be a vast, interactive network where perception and existence are deeply intertwined. Every time we measure, record, or even think about the universe, we're not just uncovering its secrets, we might be helping to write them. And that raises a question as beautiful as it is unsettling. If a tree falls in a quantum forest with no one to observe it, does it make a sound, or does it wait, suspended in possibility, until someone listens? Deep in the static of space, there are whispers so powerful they can outshine an entire galaxy for just a fraction of a second. Bursts of radio waves so intense, they travel billions of light years to reach us, then vanish without a trace. These are fast radio bursts, or FRB, some of the most enigmatic signals in the cosmos. Lasting mere milliseconds, each burst packs as much energy as the sun emits in days, yet their origins remain one of astronomy's greatest puzzles. What makes them even stranger, a handful of these bursts don't just fire once, they repeat, often in eerily precise intervals, like a cosmic metronome ticking across the void. Take FRB 121102, the first repeating burst ever discovered. Every 157 days, like clockwork, it erupts in a frenzy of radio waves, then falls silent. Other repeaters follow their own rhythmic patterns, some every 16 days, others in irregular but predictable cycles. It's as if the universe is sending signals in Morse code, but we're missing the cipher. The precision of these intervals defies most natural explanations. Colliding neutron stars or evaporating black holes, the usual suspects for one-off bursts, can't account for such regularity. So what could? One tantalizing possibility is magnetars, neutron stars with magnetic fields so strong, they could strip the electrons from your atoms from halfway across the galaxy. When these stellar corpses twist and crack under magnetic stress, they might unleash bursts of energy in rhythmic spasms. Yet even this theory falters when faced with the sheer power of some FRBs. Could they be the death throes of exotic objects we've yet to discover, like cosmic strings, theoretical defects in spacetime left over from the Big Bang? Or perhaps the beams of alien light sails, as some have speculated, though that remains firmly in the realm of speculation. Then there's the strangest clue of all. Some FRBs are polarized, their radio waves twisted in spirals, as if scrambled by traversing immense magnetic fields or dense plasma clouds. This polarization hints they've journeyed through environments far more extreme than interstellar space, maybe near the event horizon of a supermassive black hole, or through the halos of distant galaxies. It's like finding a message in a bottle, only to realize the paper inside is scorched and warped from conditions we can barely imagine. But here's what truly unsettles astronomers. FRBs aren't just cosmic oddities. They might be tools, because these bursts traverse such vast distances. They interact with the sparse matter between galaxies, leaving faint imprints of their journey. By decoding these fingerprints, scientists can map the universe's hidden scaffolding, the ionized gas and dark matter we've never seen directly. In a way, FRBs are like flashes of lightning in a cosmic storm, illuminating the invisible structures around us for the briefest instant. Whether they're natural or something more, one thing's clear: these bursts are rewriting the rules. Every time a new FRB crackles to life in our telescopes, it's a reminder that the universe is far stranger, far more inventive than we've dared to dream. And the patterns they carry, those precise, repeating intervals, might be the first notes of a symphony we're only beginning to hear. What if everything around you, the stars, the oceans, even your own hands, wasn't truly three-dimensional, but a projection, like a movie playing on the surface of an immeasurably distant screen? This isn't science fiction. It's the holographic principle, one of the most radical ideas in modern physics, suggesting that our universe's richness might be an illusion, a cosmic magic trick encoded on a two-dimensional boundary at the edge of space. The theory traces its roots to an unexpected place: black holes. When physicists calculated how much information a black hole could hold, they made a startling discovery. The maximum amount of data isn't determined by its volume, as you'd expect, but by the area of its event horizon, the surface of its point of no return. It's like realizing a hard drive's storage capacity depends not on how thick it is, but on the label stuck to its surface. This bizarre connection between surface and content led theorists to a jaw-dropping possibility. If a black hole's interior can be fully described by information painted on its boundary, maybe the entire universe works the same way. Imagine the cosmos as a hologram, the 3D world we experience, the depth of a canyon, the curve of a planet, would be like the image floating above a credit card's holographic sticker. The real universe, in this view, exists as flickering bits of data on a flat, distant shell, perhaps at the edge of the observable universe or even at the Big Bang's afterglow. Every particle, every force would just be pixels in a grand cosmic projection. Support for this idea comes from some of physics' most cutting-edge experiments. When scientists simulate quantum systems entangled across space, they find the math mirrors the equations describing black hole horizons, as if entanglement itself is stitching together a holographic reality. Even the cosmic microwave background, that ancient light from the universe's infancy, shows patterns that some researchers argue could be shadows of a two-dimensional code imprinted at the beginning of time. But the holographic principle isn't just about geometry. It challenges our deepest assumptions about reality. If true, it means the solidity of the world is an emergent property, like the wetness of water emerging from countless molecules. Your sense of depth, of distance, would be a kind of collective hallucination, a trick played by the way information interacts across the hologram's surface. Space itself might not be fundamental, just a useful illusion that helps us navigate the projection. Skeptics argue that the holographic principle, while mathematically elegant, lacks direct experimental proof. Yet others counter that we've already seen hints in unexpected places. Take quantum entanglement's spooky connections, where particles instantly influence each other across vast distances. In a holographic universe, this makes perfect sense. The particles aren't really far apart, but adjacent on the deeper code layer, like two dots drawn side by side on a piece of paper that only appear separated when you fold the paper into 3D. The implications are staggering. If reality is a hologram, then black holes aren't just cosmic oddities, they're windows into the universe's true nature. The Big Bang might not have been an explosion in space, but a rendering process, like a projector flickering to life. Even time itself could be part of the illusion, a narrative woven by the hologram to make sense of changes in the underlying data. So the next time you look up at the night sky, consider this. Those stars might not be distant suns, but pixels in the grandest display of all. A cosmic screen painting a universe so convincing, we've spent millennia believing it was real. The holographic principle doesn't just rewrite physics, it invites us to question whether we're inhabitants of a universe or players in a simulation so vast, its boundaries are written in the fabric of reality itself. Out of all the celestial coincidences in our solar system, none is as visually stunning or as statistically improbable as the perfect alignment of the moon and sun during a total eclipse. Here we have two objects with absolutely nothing in common. The sun, a raging ball of plasma 860,000 miles wide, and the moon, a cold, airless rock just 2,100 miles across. The sun is 400 times larger than the moon, yet by sheer cosmic chance, it's also 400 times farther away. The result, when they cross paths in our sky, they appear almost identical in size, allowing the moon to precisely blot out the sun's blinding disk while leaving its fiery corona shimmering around the edges like a halo. This perfect match isn't just rare, it's borderline miraculous. If the moon were slightly larger or closer, eclipses would plunge Earth into abrupt darkness, obscuring the corona entirely. If it were smaller or farther away, we'd never experience totality at all, just an annular ring of fire eclipse with the sun peeking around the moon's silhouette. Yet here we are on a planet where the math works out exactly right. The odds of this precise balance occurring naturally, astronomers estimate them at less than 1 in a billion across the universe. So how did we get so lucky? One camp argues it's pure chance, a fluke of orbital mechanics that Earth just happened to win. After all, the moon hasn't always been at its current distance. Tidal forces are slowly pushing it away by about 1.5 inches per year. Rewind 400 million years, and the moon would have loomed too large for perfect eclipses. Fast forward 600 million more, and it'll be too distant to fully cover the sun. We're living in a vanishingly narrow window where the geometry aligns, like catching a train the moment its doors open, but others see something deeper at play. The moon's role in eclipses isn't just a spectacle, it's been a catalyst for scientific discovery. Without total eclipses, we might never have confirmed Einstein's theory of relativity, which relied on the sun's blocked light to reveal how its gravity bends starlight. The corona, only visible during totality, has unveiled secrets about solar winds and magnetic fields. Even the moon itself, some theorists suggest, is freakishly large for a planet of Earth's size, likely born from a cataclysmic collision that reshaped our world's destiny. Could these factors hint at a universe that, in some subtle way, encourages conditions ripe for discovery? Then there's the anthropological angle. Perfect eclipses have shaped human culture for millennia, inspiring myths, terrifying armies into retreat, and even helping historians pinpoint ancient dates. It's as if this cosmic quirk was tailor-made to spark curiosity, awe, and scientific inquiry, a built-in puzzle waiting for civilizations advanced enough to decode it. Whether by accident or design, the moon and sun's precise symmetry doesn't just defy odds. It invites us to look closer, to question whether the universe plays favorites, or if we're simply the ones here to notice. Among the thousands of exoplanets discovered beyond our solar system, one pattern keeps reappearing: worlds locked in perfect orbital synchrony, dancing around their stars like notes in a cosmic symphony. Take TRAPPIST-1, a star system 39 light-years away with 7 Earth-sized planets. Their orbits aren't random. They're arranged in resonant chains, where each planet's year relates to its neighbors in simple whole number ratios. For every 2 orbits one planet completes, the next makes 3, creating a rhythmic pattern as precise as a metronome. This isn't rare. From Kepler's catalogue to newer discoveries, resonant systems pop up again and again, as if the universe has a favorite rhythm for arranging planets. The math behind these resonances is hauntingly elegant. Picture a pendulum swinging its motion regular, predictable. Now imagine that stability scaled up to planetary orbits, where gravitational tugs between worlds keep them locked in step, preventing chaotic collisions. In TRAPPIST-1 case, the resonances are so tight that if you could stand on one planet, you'd watch the others pass at the same points in their orbits, cycle after cycle, like gears in a celestial clock. This precision suggests something extraordinary. Planetary systems might not form in chaos, but in harmony, with gravity sculpting orbits into mathematical poetry. Yet here's the puzzle. While resonances stabilize systems over time, they're fragile. A passing star, a rogue planet, even the gentle nudge of interstellar gas could disrupt them. So how do so many systems retain these delicate arrangements for billions of years? Some astronomers argue it's a natural outcome of planet formation, a disk of gas and dust swirling around a young star, with nascent planets migrating inward until their gravitational interactions lock them into resonance. It's like marbles rolling in a bowl, settling into the lowest energy configuration, but others see hints of something more. Could there be undiscovered physics at play, perhaps subtle interactions between planets and lingering magnetic fields in their star's debris disk? Or might these patterns be fossils of a deeper order, imprinted during the system's birth? The implications ripple beyond astronomy. Resonant orbits challenge our assumptions about how unique our solar system is. Unlike TRAPPIST-1 harmonious worlds, Earth and its neighbors follow orbits that look almost haphazard by comparison. Does this mean our system is the outlier, or that resonances erode over time, leaving behind the irregularity we see today? Even more provocative, if resonant systems are more stable, could they also be more likely to harbor life? Their predictable climates, free from the wild orbital swings that trigger ice ages or scorching heat, might offer safer cradles for biology to emerge. Then there's the music of it all. The ratios governing these orbits, 2 to 3, 3 to 4, mirror the intervals found in musical chords. It's as if the universe composes planetary systems using the same mathematical scaffolding that builds symphonies. Whether this is coincidence or a whisper of something deeper, one thing's clear: the cosmos has a rhythm, and we're only beginning to hear the beat. Every resonant exoplanet is another verse in a song written in gravity's hand, inviting us to listen closer. Saturn's rings, those dazzling loops of ice and rock, have long been one of the solar system's most mesmerizing sights. But recent observations have revealed something even more astonishing: they're hotter than they should be. According to the laws of thermodynamics, the rings should absorb sunlight and radiate heat at predictable levels based on their composition and distance from the sun. Yet data from NASA Cassini spacecraft showed they're emitting far more infrared energy than expected, as if an invisible furnace were humming just beneath their icy surface. This isn't just a minor discrepancy. The excess heat is significant enough to defy conventional explanations. Sunlight alone can't account for it, nor can reflected light from Saturn itself. Some researchers have turned to dark matter as a possible culprit, speculating that if these mysterious particles interact weakly with ordinary matter, they might accumulate in Saturn's gravitational field, colliding and annihilating within the rings to release energy. It's a radical idea, but not impossible. Dark matter's gravitational effects are well documented across the cosmos, and if it clusters around massive objects like Saturn, even rare interactions could produce detectable heat. Then there's the possibility of exotic particles, hypothetical entities like actions or sterile neutrinos, which could permeate space and transfer energy in ways we don't yet understand. Saturn's rings, with their trillions of tiny particles, might act like a giant detector, capturing and converting this hidden energy into heat. Think of it like holding a sheet of paper in front of a fireplace. You'd expect it to warm slowly. But if unseen embers were scattered across its surface, the paper would heat unevenly, just as the rings seem to. But here's where it gets even stranger. The heat isn't distributed uniformly. Some sections of the rings, particularly the denser regions, glow brighter in infrared than others. This patchiness suggests the heating mechanism isn't passive but dynamic, possibly tied to interactions with Saturn's magnetic field or even electrical currents induced by charged particles raining down from the planet's radiation belt. Jupiter's auroras, for example, generate immense heat through similar processes. Could Saturn's rings be hiding their own version of this phenomenon? The implications stretch far beyond Saturn. If dark matter or exotic particles are truly at work here, the rings could become a unique laboratory for studying physics we can't replicate on Earth. Unlike distant galaxies or abstract simulations, Saturn's rings are close enough to probe directly, offering a tangible way to test theories that otherwise remain speculative. Even if the answer turns out to be something more mundane, like micrometeoroid impacts or internal friction within the ring particles, the anomaly still challenges our understanding of how energy flows in planetary systems. What makes this mystery so compelling isn't just the unsolved puzzle, it's the reminder that even in our own cosmic backyard, there are forces at work we've yet to grasp. The next time you gaze at Saturn through a telescope, remember, those serene, glittering bands might be hiding a secret, one that could rewrite the rules of physics as we know them. The cosmic microwave background is supposed to be the ultimate equalizer, a nearly uniform afterglow from the Big Bang that looks the same in every direction, confirming the universe has no special place or orientation. But when scientists analyzed its subtle temperature fluctuations, they stumbled upon something that sent chills down their spines, an eerie alignment dubbed the axis of evil. This mysterious pattern shows that the warm and cold spots in the cosmic microwave background aren't entirely random. Instead, they appear to correlate ever so slightly with the plane of our solar system, as if the universe is subtly nodding in our direction. This discovery should be impossible. The Copernican principle, one of the cornerstones of modern cosmology, tells us Earth isn't at the center of anything, we're just another speck in an indifferent cosmos. Yet the axis of evil suggests a faint but detectable link between the largest-scale structure of the universe and our own tiny neighborhood. It's like discovering that the cracks in a dried-up lake bed somehow mirror the pattern of tiles in your kitchen. The odds of this happening by pure chance, astronomers calculate them at less than 1 in 1,000. So what's really going on? One possibility is that we're seeing the ghostly imprint of an ancient cosmic influence, something that shaped the early universe in a way we've yet to comprehend. Inflation, the rapid expansion thought to have smoothed the cosmos after the Big Bang, might not have been perfectly uniform. Tiny asymmetries in that expansion could have left behind a preferred direction, like invisible brushstrokes frozen in spacetime. Alternatively, the axis of evil might hint at structures beyond our observable universe, perhaps a neighboring bubble of space in the multiverse whose gravity subtly tugged on ours, leaving a faint gravitational fingerprint. Then there's the unsettling alternative, that we're witnessing the limits of our own perception. Could there be some systematic error in how we measure the cosmic microwave background, some quirk of satellite positioning or interstellar dust that creates the illusion of alignment? The Planck satellite, our most precise mapper of this ancient light, has confirmed the anomaly exists, but the debate over its meaning rages on. Skeptics argue it's a statistical fluke, a cosmic Rorschach test where we're seeing patterns that aren't truly there. Yet every time researchers try to dismiss it, the axis of evil stubbornly refuses to vanish, lingering like a whisper at the edge of detection. The implications ripple far beyond astronomy. If the universe truly has a preferred axis, if it's not the same in all directions, then our understanding of its origins, evolution, and even its fate might need rewriting. The laws of physics as we know them assume isotropy, the idea that the cosmos has no special direction. But what if that assumption is wrong? Could this explain other anomalies like the dark flow of galaxies or the unexpected alignments of quasars? Or is the axis of evil a clue that we're missing a deeper layer of reality? One where the universe isn't just expanding but spinning, vibrating, or even breathing in ways we've yet to imagine. Whatever the answer, this much is clear. The cosmic microwave background isn't just a relic of the past. It's a mirror reflecting back at us the unnerving possibility that the universe isn't as indifferent as we thought. Whether it's a flaw in our models, a footprint of something greater, or just a trick of the light, the axis of evil forces us to confront a humbling truth. We might not be at the center of the cosmos, but we're certainly entangled in its mysteries in ways we're only beginning to understand. Imagine flipping a coin and catching it mid-air, over and over, so fast that it never lands, forever suspended between heads and tails. That's the essence of the quantum Zeno effect, one of the most mind-bending phenomena in physics. At the quantum scale, particles exist in a haze of possibilities. An electron might be here, there, or everywhere at once until measured when it chooses a definite state. But here's the twist. If you observe that particle relentlessly, bombarding it with measurements, something astonishing happens. It freezes. Like a deer caught in headlights, the particle locks into place, as if reality itself hesitates under the weight of our gaze. This isn't just theoretical. In labs, scientists have used rapid-fire laser pulses to trap atoms in unstable states indefinitely, defying their natural decay. It's as if the act of watching presses pause on quantum chaos, stretching moments into eternity. The implications ripple far beyond the lab. If frequent observation can alter reality's behavior, does that mean consciousness, or at least interaction, plays an active role in shaping the universe? Some interpretations of quantum mechanics suggest yes. In the participatory universe model, reality isn't a fixed stage but a dynamic performance, where observers aren't just audience members but co-creators, collapsing probabilities into tangible existence through the act of measurement. Yet skeptics push back. They argue the Zeno effect isn't about consciousness but interaction. Any physical disturbance, even from a machine, can trigger it. The universe doesn't care if a human is watching. It responds to energy exchanges, whether from a detector or a stray photon. Still, the eerie parallel remains. The more we scrutinize quantum systems, the more they resist change, as if reality thrives on ambiguity and shies away from scrutiny. This paradox raises a haunting question. Could the Zeno effect be operating on a cosmic scale? If the universe began as a seething quantum foam, could some primordial form of observation, perhaps from other particles or fields, have stabilized matter into the structures we see today? It's a wild idea, but not impossible. After all, black holes with their event horizons act like natural measurement devices, locking information onto their surfaces in ways that eerily mirror the Zeno effect. Whether it's a quirk of math or a clue to something deeper, one thing's certain: the quantum Zeno effect blurs the line between the observer and the observed. Every measurement we make doesn't just reveal reality, it might just be holding it together, and that leaves us with a humbling thought. The universe isn't just something we discover. It's something we participate in, one observation at a time. stretching across the cosmos like invisible threads, vast clouds of hydrogen, the universe's most abundant element, drift through the darkness, silent and seemingly chaotic. But when radio telescopes pierce the veil, these clouds reveal something astonishing: intricate, double helix structures twisting through space like strands of cosmic DNA. One of the most striking examples lies near the center of our galaxy, where a 300-light-year-long filament coils with eerie precision, its spiral shape mirroring the very blueprint of life. The resemblance is so uncanny, it's hard to dismiss as mere chance. So what's really shaping these gaseous giants into such familiar forms? The answer might lie in the invisible forces threading the galaxy. Magnetic fields woven through interstellar space like an immense spiderweb could be sculpting these hydrogen clouds into helical spirals. Picture a ribbon twisting in the wind. The same principle applies, but on a scale so vast, it takes light centuries to traverse a single curve. As charged particles within the hydrogen interact with these magnetic fields, they spiral along the lines of force, creating the illusion of a celestial double helix. This isn't just poetic symmetry, it's physics in action, a dance of energy and matter playing out in slow motion across the void. Yet the implications go far beyond simple mechanics. The presence of these structures raises a provocative question. If the universe naturally produces patterns resembling life's fundamental code, could there be a deeper connection between the macrocosm and the microcosm? Some researchers speculate that the universe might inherently favor certain geometries, whether in the curve of a galaxy, the twist of a hurricane, or the coil of a molecule, because they represent the most stable, energy-efficient configurations. In other words, DNA's double helix might not be unique to biology, but a universal motif written into the fabric of reality itself. Others take the idea further. Could these hydrogen helices be more than just pretty shapes? Theoretical models suggest that under extreme conditions, like those near supermassive black holes, complex molecules can form in space, including the precursors to amino acids. If that's true, these cosmic spirals might be cradles of prebiotic chemistry, quietly assembling the raw materials for life in their swirling depths. It's a tantalizing thought. The same forces that sculpt galaxies could also be quietly setting the stage for biology, weaving the universe's hidden potential into every twist and turn. But skeptics urge caution. While the visual resemblance is striking, they argue, it doesn't necessarily imply a deeper link between cosmic structures and biological ones. After all, nature reuses patterns because they work, not because they carry hidden meaning. A spiral is just an efficient way to pack a lot of material into a small space, whether it's a hurricane, a galaxy, or a strand of DNA. The universe isn't trying to mimic life. It's simply obeying the same physical laws that shape everything from atoms to star clusters. Still, the coincidence is hard to ignore. When we look at these hydrogen helices, we're seeing more than just gas and magnetism. We're glimpsing a universe that seems to echo itself across scales, from the smallest cells to the largest clouds in space. Whether that's a sign of something deeper, a universal language of structure, a hidden layer of information encoding, or simply a beautiful accident, one thing's certain: the cosmos has a flair for the dramatic. And every time we discover another of these cosmic double helixes, we're reminded that the universe's greatest mysteries might not just lie in the unknown, but in the uncanny familiarity of its designs. The Sun, that fiery engine at the heart of our solar system, has always been a tempest of chaos, a churning ball of plasma where magnetic fields twist, snap, and unleash storms of radiation without warning. But hidden in that chaos is a puzzle that defies everything we know about solar physics. Sometimes solar flares, those violent eruptions of energy, don't just explode randomly. They erupt in perfect sync, like distant fireworks timed to the same unseen cue, even when they're separated by hundreds of thousands of miles on the sun's surface. These aren't just coincidences, they're cosmic choreography, and they hint at a level of organization we've barely begun to understand. Take the events of July 23, 2012. Two massive solar flares erupted almost simultaneously, one near the sun's north pole, the other near its south. According to standard models, these regions shouldn't have been magnetically connected. The flares were too far apart, separated by a labyrinth of magnetic field lines that should have isolated them, yet they fired in eerie unison, as if an invisible conductor had raised a baton. Scientists scrambled for explanations. Could there be hidden magnetic tunnels threading through the sun, linking distant regions like secret passageways? Or was something even stranger at play, a phenomenon we haven't yet imagined? One leading theory points to global oscillations, subtle vibrations rippling through the sun's interior, much like sound waves resonating through a bell. These oscillations, driven by the sun's rotation and convective currents, might act as cosmic metronomes, synchronizing flare activity across vast distances. Imagine tapping a wine glass and watching droplets on opposite sides shiver in response. The sun could be doing something similar, with magnetic energy building and releasing in harmony with these deep, rhythmic pulses. But skeptics argue this doesn't fully explain the precision of the synchrony. If oscillations were the sole culprit, we'd expect more randomness, not the near-perfect timing observed. That's led some researchers to explore even wilder ideas. Could the sun's magnetic field operate on principles akin to quantum entanglement, where changes in one region instantaneously affect another, regardless of distance? It sounds outlandish, but similar phenomena have been proposed in astrophysics, like the way black holes might be connected through wormholes or higher dimensional bridges. Then there's the tantalizing possibility that we're seeing the fingerprints of a deeper, hidden structure, a kind of solar internet where magnetic energy flows along unseen pathways. Recent simulations suggest the sun's magnetic field might self-organize into fractal networks, with smaller structures nested inside larger ones, all resonating in harmony. If true, this would mean the sun isn't just a turbulent ball of gas, it's a finely tuned system, balancing chaos and order in ways we're only beginning to decode. What makes these synchronized flares so unsettling isn't just the mystery, it's the implication that the sun might be more than the sum of its parts. We think of it as a collection of plasma and magnetic fields, but what if it functions as a unified organism with rhythms and connections we can't yet measure? Every time a pair of flares erupt in unison, they're not just defying our models, they're inviting us to rethink the very nature of stars. And if the sun, our closest stellar neighbor, holds secrets this profound, what else is the universe hiding in plain sight? Of all the particles in the universe, none are as elusive or as baffling as neutrinos. Trillions of these ghostly particles pass through your body every second, leaving no trace as they zip through solid rock, oceans, even entire planets without slowing down. Their near invisibility earned them the nickname ghost particles, but it's their ability to shape-shift that truly defies physics. As neutrinos travel vast distances, they oscillate between three distinct flavors: electron, muon, and tau, like a chameleon cycling through colors mid-stride. This metamorphosis shouldn't be possible if neutrinos were massless, as the standard model of particle physics originally assumed. Yet experiments from deep underground labs to Antarctic ice sheets have proven it happens constantly, forcing scientists to rewrite the rules of reality. The implications ripple far beyond textbook corrections. Neutrino oscillations suggest these particles have mass, an idea that once seemed heretical. Their tiny but non-zero weight hints at physics beyond the standard model, possibly including undiscovered particles or forces. Some theorists speculate neutrinos could be Majorana particles, meaning they're their own antiparticles, a property that might explain why the universe contains more matter than antimatter. Others propose they interact with hypothetical sterile neutrinos, shadowy counterparts that only feel gravity, potentially serving as dark matter candidates. The math even allows for neutrinos to tunnel through extraspatial dimensions, briefly disappearing from our universe before reappearing elsewhere, like quantum phantoms slipping through walls. Then there's the eerie timing. When a neutrino detector in Japan caught particles fired from an accelerator 295 kilometers away, they arrived 60 nanoseconds earlier than light speed should allow. Though the anomaly was later attributed to faulty wiring, the mere possibility of faster-than-light neutrinos sent shockwaves through physics. Could these particles be bending space-time in ways we don't understand? Or tapping into hidden dimensions where distance and time behave differently? What makes neutrinos so tantalizing isn't just their oddness, it's their ubiquity. Born in the hearts of stars, supernova, and even Earth's radioactive crust, they're cosmic messengers carrying secrets from the most extreme environments. A supernova's neutrinos reach us hours before its light, offering early warnings of stellar explosions. Solar neutrinos provide a real-time peek into the sun's fusion furnace. And high-energy neutrinos detected at the South Pole trace back to violent events like flaring black holes, painting a map of the universe's most energetic phenomena. Yet for all their abundance, neutrinos remain maddeningly hard to study. Catching one is like finding a specific grain of sand in a desert the size of Jupiter. Modern detectors use Olympic-sized pools of ultra-pure water or massive blocks of ice lined with sensors, waiting years for the rare flash when a neutrino finally interacts. But each capture rewrites our understanding a little more. The more we learn, the clearer it becomes. Neutrinos aren't just passive bystanders in the cosmos. They might be the key to unlocking dimensions we've yet to imagine, a hidden layer of reality woven between the particles we know. Every oscillation, every flavor change is a whisper from the universe's shadow world, urging us to look deeper. Somewhere in the depths of space, hidden behind the thick veil of our own Milky Way stars and dust, lies a gravitational monster so powerful it's dragging entire galaxies, including ours, toward it at over 14 million miles per hour. Astronomers call it the Great Attractor, and it's one of the most perplexing mysteries in modern cosmology. Imagine throwing a ball into the air, only to watch it curve sideways instead of falling back down. That's essentially what's happening to our local group of galaxies as we're pulled toward this invisible cosmic magnet. The strangest part, we can't see what's doing the pulling. The Great Attractor sits in a region called the Zone of Avoidance, where the dense plane of the Milky Way blocks our view like a cosmic blindfold. All we know is that something with the mass of tens of thousands of Milky Ways must be lurking there, bending the paths of galaxies across hundreds of millions of light years. Initial observations suggested a massive cluster of galaxies might be responsible, but even the largest known clusters don't pack enough punch to explain the sheer scale of this gravitational tug-of-war. Here's where it gets even weirder. Recent surveys using infrared and X-ray telescopes which can peer through galactic dust have revealed that the Great Attractor might just be the tip of the iceberg. Behind it lies an even larger structure, the Shapley supercluster, a sprawling metropolis of galaxies containing nearly 10 times the mass of our local supercluster. Some researchers think this colossal concentration of matter could be amplifying the great attractor's pull, like a hidden mountain range distorting the flow of a river. But others argue the math still doesn't add up. Shapley's gravity alone can't account for the observed motion. Could dark matter be the missing piece? This invisible substance, which outweighs normal matter 5 to 1, might form an ultra-dense knot in this region, warping space-time more intensely than visible matter ever could. Alternatively, the great attractor might not be a single object at all, but the focal point where multiple cosmic flows converge, a gravitational whirlpool where the large-scale structure of the universe funnels galaxies like leaves caught in a drain. Then there's the most mind-bending possibility of all, that the great attractor is a signpost pointing to something even grander. Some models of the universe suggest that these massive flows are part of a web stretching beyond our observable horizon, driven by structures so vast they make superclusters look like specks. If true, we're not just being pulled toward a hidden attractor, we're caught in a cosmic current that flows toward realms we may never see, following gravity's silent call into the unknown. Every galaxy caught in this flow carries a story written in starlight, a testament to the invisible forces shaping our corner of the cosmos. The great attractor isn't just a destination, it's a reminder that even on the grandest scales, the universe still holds secrets just out of view, waiting for the right moment to pull us closer to the truth. At the heart of particle physics lies one of the most elegant symmetries in nature. For every particle we've discovered, there exists a mirrored counterpart with opposite properties. Electrons have positrons, protons have antiprotons, even neutrinos have antineutrinos. These antimatter twins are nearly perfect reflections, identical in mass but flipped in charge and quantum states. When matter and antimatter meet, they annihilate in a burst of pure energy, leaving behind only photons as tombstones to their existence. This dance of creation and destruction should have played out perfectly after the Big Bang, with equal amounts of matter and antimatter canceling each other out. Yet here we are, in a universe made almost entirely of matter, a staggering asymmetry that defies everything we know about cosmic bookkeeping. The mystery deepens when we examine the numbers. According to the Standard Model, the early universe should have produced matter and antimatter in perfectly balanced quantities. Even accounting for random fluctuations, the slight excess of matter needed to build galaxies, stars, and us would require a discrepancy of just 1 part in a billion. But experiments reveal something far more puzzling. Not only does antimatter behave differently in subtle ways, like the way certain particles decay, but the imbalance appears far too large to explain through known physics. It's as if the universe opened with 2 identical vaults of gold, then mysteriously emptied one entirely while leaving the other untouched. So where did all the antimatter go? One leading theory points to a phenomenon called charge parity violation, where the laws of physics treat matter and antimatter slightly differently. We've observed this in quarks, the building blocks of protons and neutrons, but the effect is too weak to account for the universe's overwhelming matter dominance. Some researchers speculate undiscovered particles, like hypothetical sterile neutrinos or actions, might have tipped the scales in the early cosmos. Others explore exotic scenarios where antimatter wasn't destroyed but exiled, perhaps hidden in distant anti-galaxies, or trapped in mirror dimensions we can't yet detect. The most tantalizing clues come from the coldest place in the universe laboratories, where scientists trap single antiparticles in magnetic fields for months at a time. By comparing the vibrational frequencies of antihydrogen atoms to their matter counterparts with mind-boggling precision, they've found near-perfect symmetry. But not quite. The slightest deviation could rewrite our understanding of cosmic history. Meanwhile, deep underground, detectors watch for the radioactive decay of protons, a process that, if observed, would prove matter isn't perfectly stable and might hint at why it survived when antimatter didn't. This isn't just academic curiosity. The absence of antimatter shapes the very fabric of reality. Had the scales balanced perfectly, the universe would be a lifeless sea of radiation. That they didn't suggest something profound, that the laws of physics contain hidden wrinkles, subtle biases woven into the quantum code that allowed matter to win the ultimate cosmic lottery. Every atom in your body, every star in the sky, exists because of this inexplicable favoritism. Solving the antimatter mystery wouldn't just fill a gap in our equations. It would reveal why anything exists at all. The universe is expanding, that much we know, but ask astronomers how fast, and suddenly the conversation turns tense. The Hubble constant, the number representing the rate of cosmic expansion, should be a fixed value, a cosmic speedometer giving us a single, definitive answer. Instead, we have a puzzle. When measured using nearby supernovas and Cepheid variable stars, the universe appears to be ballooning about 10% faster than when calculated from the afterglow of the Big Bang, the cosmic microwave background. This discrepancy isn't a minor rounding error. It's a glaring rift in our understanding of reality, one that's persisted for over a decade despite increasingly precise instruments. Why does this matter? Imagine trying to bake a cake where the oven's temperature dial gives two different readings depending on whether you check it before or after preheating. You'd question the tool, the oven, maybe even the laws of thermodynamics. That's where cosmology stands today. The cosmic microwave background, frozen in time from 380,000 years after the Big Bang, suggests an expansion rate of around 67 kilometers per second per megaparsec. But observations of supernovas in the modern universe peg it closer to 73. The gap might seem small, but in a field where measurements are refined to decimal places, it's a chasm. Either we're missing something fundamental about how the universe works, or our tools are revealing a flaw in the very foundations of physics. One tantalizing possibility is that dark energy, the mysterious force accelerating cosmic expansion, isn't constant after all. What if it's evolving, growing stronger over time? This could explain why modern measurements show faster expansion than early universe data predicts. Alternatively, there might be undiscovered particles like a new type of neutrino, subtly altering the cosmos's trajectory. Some theorists even speculate that our universe collided with a bubble of exotic physics in its infancy, leaving behind ripples that skewed the expansion rate in our local neighborhood. Then there's the radical notion that we've misjudged the cosmic microwave background itself. What if tiny systematic errors in how we interpret its faint whispers have led us astray? Or worse, what if the early universe wasn't as uniform as we thought, and our corner of space is unusually dense, throwing off local measurements like a funhouse mirror? The stakes couldn't be higher. If the Hubble tension is real, it might mean that Einstein's theory of relativity, the bedrock of modern cosmology, needs a tweak, or that we're on the brink of discovering a whole new layer of physical law. Every new telescope, from the James Webb Space Telescope to next-generation cosmic microwave mappers, is now hunting for clues to resolve this crisis. The answer won't just settle a scientific debate, it could rewrite the story of the universe's birth, life, and ultimate fate. Whether the tension reveals new particles, dark energy's secrets, or something even stranger, one thing's clear: the cosmos is holding out on us. And the harder we look, the more it seems to whisper that our map of reality is still missing whole continents of understanding. Most galaxies come in familiar shapes: spirals with their graceful arms, ellipticals like glowing orbs, or chaotic irregulars. But every now and then, the universe throws us a curveball. Take Hoag's object, a galaxy so bizarre it looks like someone dropped a cosmic bullseye into deep space. At its core sits a golden sphere of ancient stars, but encircling it, separated by a vast, empty gap, floats a perfect ring of younger, blue stars, a structure so symmetrical it defies conventional explanations. This isn't some artist's rendering, it's a real celestial anomaly, and it's not alone. Astronomers have catalogued dozens of these ring galaxies, each one a puzzle wrapped in starlight. The leading theory suggests these rings are cosmic wreckage, ghostly echoes of violent collisions. Picture a smaller galaxy plunging straight through the heart of a larger one, like a bullet through an apple. The gravitational shockwave would fling stars outward in an expanding ripple, leaving behind a temporary ring before fading into chaos. Computer simulations support this idea, showing how such collisions can sculpt rings lasting hundreds of millions of years. But here's the catch. Hoag's object shows no signs of a recent impact. No twisted debris, no disturbed gas clouds, just that eerie, pristine circle floating in perfect isolation. That's led some researchers to consider darker possibilities. Could these rings be signatures of exotic physics, like dense knots of dark matter orbiting galactic cores? If dark matter interacts in ways we don't yet understand, it might sculpt stars into these precise formations without the need for collisions. Others point to instabilities in galactic magnetic fields, which could theoretically channel star formation into narrow, ring-like bands. There's even speculation about resonant orbits where stars align in specific patterns over billions of years, like sand grains arranging themselves on a vibrating drumhead. But the plot thickens when we look beyond single rings. A handful of galaxies like NGC 2950 sport multiple concentric rings stacked like tree rings across cosmic timescales. These layered structures suggest periodic bursts of star formation, as if something, perhaps rhythmic infalls of intergalactic gas, pulsed through the galaxy at regular intervals. It's as if the galaxy itself has a heartbeat, with each pulse leaving behind a shimmering stellar fingerprint. The most tantalizing clue might lie in polarization. Recent observations reveal that some ring galaxies emit light with a distinct twisted signature, hinting at massive, organized magnetic fields spiraling through their structures. If confirmed, this could mean the rings aren't just passive bystanders but active participants in some larger electromagnetic dance, one where invisible forces choreograph the motions of stars. Whether sculpted by violence, dark matter, or hidden magnetism, these galactic rings challenge our assumptions about how galaxies live and evolve. They're not just celestial oddities, they're cosmic experiments testing the limits of gravity, turbulence, and time. Every perfect circle in the void whispers the same question: how well do we really understand the forces shaping our universe? And if something as simple as a ring can defy explanation, what else is waiting to upend everything we think we know? Beneath the smooth fabric of space-time we take for granted lies a hidden chaos, a frothing, turbulent sea where reality itself flickers in and out of existence. This is quantum foam, the bizarre predicted state of space-time at scales 1 trillion times smaller than an atom, where the laws of physics as we know them dissolve into uncertainty. Imagine the surface of a calm lake, seemingly solid and unbroken, but zoom in close enough and you'll see it's actually a churning frenzy of molecules colliding and separating. Quantum foam suggests space-time behaves the same way, with tiny regions bubbling into existence only to vanish moments later, like a cosmic simmering pot where space and time lose all meaning. What fuels this frenzy? Heisenberg's uncertainty principle, which allows particles to borrow energy from the vacuum of space for fleeting instants. These virtual particles erupt in particle-antiparticle pairs, annihilating each other so quickly they evade detection. Normally, this dance remains invisible, but at the Planck scale, the smallest possible unit of spacetime, these fluctuations warp the very geometry of reality, twisting it into a labyrinth of microscopic wormholes, tunnels, and bubbles. It's as if the universe's foundation is built on shifting sand, constantly rearranging itself beneath our feet. The implications are staggering. If spacetime is foamy, it could bridge the greatest divide in modern physics, the clash between quantum mechanics and general relativity. Einstein's theory paints gravity as the smooth curvature of spacetime, while quantum mechanics deals in discrete, jumpy particles. Quantum foam might be where these worlds collide, a realm where gravity itself becomes quantized, its force carried by hypothetical particles called gravitons dancing in the foam. Some theories, like loop quantum gravity, propose spacetime isn't continuous but made of tiny, indivisible loops or pixels, with the foam representing the glitches between them. Others suggest the foam's chaotic nature could explain dark energy, with virtual particles pushing space apart faster and faster. But how do we test something so infinitesimal? One approach relies on cosmic messengers, high-energy photons from distant gamma-ray bursts. If spacetime is foamy, these photons should stumble through its bumps and twists like cars on a rocky road, arriving at Earth slightly out of sync depending on their wavelengths. Experiments using telescopes like the Fermi Gamma-Ray Space Telescope have hunted for these delays, but results remain inconclusive, hinting that if foam exists, its bubbles are far smaller than predicted. Another avenue exploits the precision of atomic clocks. Placed in orbit, these clocks could detect minute variations in time's flow caused by foam-induced fluctuations, like a stopwatch ticking erratically in a storm. The wildest possibility, quantum foam might not just be a microscopic quirk, it could scale up. Some models suggest that in extreme environments like black hole singularities or the primordial universe, foam-like structures might expand to macroscopic sizes, rendering spacetime a fractal mosaic where cause and effect break down. Imagine stepping into a black hole and finding not a point of infinite density, but a frothing quantum soup where directions like inside and outside lose all meaning. Whether it's the key to unification or just another cosmic dead end, quantum foam forces us to confront a humbling truth. The universe's most fundamental layer might be a place of pure anarchy, where geometry fractures and time stutters. Every virtual particle popping into existence is a reminder that reality, for all its apparent solidity, is built on a foundation of chaos, and untangling that chaos might be the only way to hear the universe's deepest whispers. Black holes have long been portrayed as cosmic dead ends, places where matter vanishes into an infinitely dense singularity, crushed beyond recognition by gravity's relentless grip. But what if that's not the whole story? A radical idea bubbling through theoretical physics suggests these gravitational monsters might hide something far stranger at their cores. Planck stars, exotic objects so dense they flirt with the very fabric of reality itself. Unlike singularities where physics breaks down entirely, Planck stars are theorized to halt collapse at the smallest possible scale, the Planck length, a distance so tiny it's a trillion times smaller than an atom. At this unimaginable scale, quantum effects could rebel against gravity's crush, creating a stable, ultra-compact orb of matter glowing with the heat of a newborn universe. The concept turns our understanding of black holes inside out. Instead of a one-way ticket to oblivion, matter falling into a black hole might encounter this fiery quantum barrier, a final stage where space and time regain their structure, however distorted. Imagine a star compressed to the size of a proton, yet containing the mass of a mountain. The energy trapped inside would be staggering, and when such an object finally decays, perhaps over billions of years, it could release a burst of radiation visible across the cosmos. Some theorists even speculate that certain gamma-ray bursts, those brilliant flashes lighting up distant galaxies, might be the dying breaths of ancient Planck stars. What makes this idea so compelling isn't just the escape from singularities, it's the potential to bridge the gap between quantum mechanics and gravity. At the heart of a Planck star, space-time wouldn't dissolve into infinity but would instead churn with quantum foam, those fleeting bubbles of reality where the ordinary rules of physics take a backseat. This could resolve one of the biggest paradoxes in black hole physics, the information paradox. If black holes truly destroy information, it violates quantum theory's insistence that information can never be lost. But if matter and energy are preserved within a Planck star's structure, even in some scrambled form, the universe's ledger might stay balanced after all. Yet the mysteries only deepen from there. How would a Planck star actually behave? Calculations suggest its surface could act like a cosmic trampoline, bouncing infalling matter back outward in a process called quantum rebound. This wouldn't happen instantly. Time dilation near a black hole's event horizon means external observers might see the rebound play out over eons, but it paints a picture of black holes not as eternal traps, but as temporary way stations in matter's journey. Some models even hint that Planck stars could be the seeds of new universes, with their unimaginable densities sparking new big bangs in hidden dimensions. Of course, proving any of this remains a monumental challenge. Planck stars would be buried deep within black holes, shielded by event horizons that cloak their secrets from view. But indirect clues might lurk in the gravitational waves rippling through space when black holes collide. If Planck stars exist, their unique structure could imprint subtle fingerprints on these waves, deviations from the smooth chirps predicted by classical physics. Future detectors like the planned Laser Interferometer Space Antenna could be sensitive enough to spot these anomalies, offering the first hints of quantum gravity in action. The Planck star hypothesis reminds us that the universe's most extreme environments might not be endpoints but portals to new physics, new dimensions, or even new cosmic cycles. Whether they're real or just a mathematical mirage, these theorized objects push us to rethink the nature of reality itself. After all, if black holes aren't the dark, featureless pits we once imagined, what else have we misunderstood about the cosmos? The answer might be hiding in the quantum heart of the abyss, waiting for us to decode its fiery language. Given the sheer number of stars in the Milky Way, some 400 billion, and the trillions of galaxies beyond it, the universe should be teeming with civilizations. Statistically speaking, even if the odds of life arising around any given star are vanishingly small, the cosmic scale should have produced countless intelligent species by now. So where is everyone? This is the Fermi Paradox, the haunting disconnect between the high probability of extraterrestrial life and the eerie silence that greets our searches. One explanation is simple: we're alone. Life might be so astronomically rare that Earth is a fluke, a cosmic lottery winner in a galaxy of barren rocks. Consider the challenges life faces just to begin. A planet must orbit in the Goldilocks zone of its star where liquid water can exist. It needs stable geology, protective magnetic fields, and the right mix of elements to spark biology. Even then, intelligence isn't guaranteed. Earth took 4.5 billion years to produce a species capable of radio telescopes, and countless evolutionary dice rolls had to land just right. If any of those steps had failed, our planet might still be home to nothing more than microbes. But another possibility is far more unsettling. What if life is common, but something stops civilizations from reaching the stars? This is the Great Filter Hypothesis, a cosmic bottleneck that prevents most species from advancing beyond a certain point. The filter could lie in our past, meaning we've already beaten extraordinary odds to emerge. Or worse, it could lie ahead, lurking in our future like a minefield. Nuclear war, climate collapse, runaway AI, any of these could be the universal traps that silence civilizations before they ever make contact. Then there's the zoo hypothesis, the idea that advanced civilizations know we're here but choose not to interfere, observing us like wildlife in a preserve. It sounds like science fiction, but if a species millions of years ahead of us exists, their motives might be as incomprehensible to us as ant behavior is to a human. They could be waiting for us to reach a certain milestone or avoiding contamination of our development, or perhaps the silence is a matter of scale. Space is vast and time is long. Civilizations might rise and fall in the blink of a cosmic eye, their signals fading before they ever cross the interstellar void. Imagine two fireflies blinking in the night, separated by miles of forest. The chances they'll ever see each other's light are slim. Our own radio signals have only traveled 100 light-years so far, a tiny bubble in the galaxy. The most unnerving answer: we're not listening the right way. Alien communication might not use radio waves at all. Advanced civilizations could rely on neutrinos, quantum entanglement, or something we haven't even imagined. Our efforts might be like scanning the ocean for smoke signals while whales sing in the depths. Whatever the truth, the Fermi Paradox isn't just about aliens. It's a mirror forcing us to confront our own fragility and rarity in the cosmos. Every silent star is a question, and the answer might change everything we think we know about our place in the universe. Time slips through our fingers like sand in an hourglass, always flowing, never pausing, and utterly indifferent to our pleas for just one more moment. Einstein shattered our classical view of time by revealing its flexibility. Clocks tick slower in strong gravity or at high velocities, proving time is woven into the fabric of space-time itself. But here's the puzzle that keeps physicists awake at night. Why does time only march forward? Why do we remember the past but not the future, when the fundamental laws of physics work just as well in reverse? Consider a cup shattering on the floor. The fragments never spontaneously reassemble into the whole cup, even though the physics of each individual particle would allow it. This irreversible directionality is called the arrow of time, and it's one of the universe's most stubborn mysteries. The classic explanation points to entropy, the tendency of systems to move from order to disorder. The early universe had unimaginably low entropy, a state of exquisite improbability, and ever since, everything has been unraveling toward chaos. But why was entropy so low to begin with? Some theorists argue it's a fluke of cosmic initial conditions, a frozen accident from the Big Bang. Others propose a far stranger idea, that time isn't fundamental at all, but an illusion emerging from deeper physics, like temperature arising from the jostling of atoms. This concept, called emergent time, suggests that what we perceive as time's flow might be a side effect of quantum entanglement. Imagine the universe as a vast network of interconnected particles. As these particles become more entangled, their shared information creates a sense of progression, a now that shifts like a spotlight moving across a stage. In this view, time isn't a backdrop to reality. It's a story the universe tells itself as it grows more complex. Experiments with quantum systems hint at this possibility. When particles entangle, their mutual correlations can act like a clock, marking intervals without any external timekeeper. Could the entire universe be running on a similar principle, with time emerging from the sheer density of quantum connections? Then there's the radical notion that time's arrow is a cosmic mirage. In block universe theory, past, present, and future exist simultaneously, a static four-dimensional landscape where our sense of movement is just a psychological artifact. Think of a DVD. The entire movie is there, but your experience of it unfolds scene by scene. If true, this would mean that free will is an illusion, and every moment from the birth of stars to the words you're reading now is already etched into space-time. Yet even this deterministic view doesn't fully explain why we experience time linearly. Some physicists speculate that consciousness itself might play a role, with our perception of time's flow tied to how our brains process information, like a projector stitching still frames into motion. The most tantalizing clues come from black holes. At their event horizons, time appears to freeze from an outsider's perspective, while inside, it might behave erratically or even loop back on itself. If time can warp so dramatically under extreme gravity, could it also fluctuate or fragment at the quantum scale? Experiments with ultra-precise atomic clocks have detected subtle time dilation effects even at millimeter distances, suggesting that time isn't just elastic, it's inherently fuzzy at the smallest scales. Whether time is fundamental or emergent, its behavior holds existential stakes. If it's truly an illusion, then aging, decay, and even death might be side effects of a deeper, timeless reality. Alternatively, if time is real but reversible in theory, could advanced civilizations someday rewind their local clocks, stitching shattered cups back together or reversing entropy itself? For now, time remains the universe's most enigmatic architect, silently shaping everything from the decay of atoms to the arc of history, all while daring us to unravel its deepest secrets. Every tick of the clock is a reminder that we're not just observers of time, but participants in its grand, unfolding mystery. What if every ancient galaxy, every fossil buried in the Earth, even the light from stars millions of light years away, were all part of an elaborate illusion? This is the unsettling premise of the Amphalos Hypothesis, a radical thought experiment suggesting the universe might be intentionally crafted to appear ancient, complete with fabricated evidence of a past that never actually occurred. The name comes from Greek mythology. Amphalos, the navel of the world, a stone Zeus supposedly placed to mark the center of existence. Just as that stone was created with the illusion of age, this idea proposes our entire cosmos could be a pre-aged construct, its history woven into its fabric like wrinkles stitched into a new pair of jeans. At first glance, the notion seems absurd. After all, we've built entire scientific disciplines on the assumption that the past leaves tangible traces: carbon-dated bones, redshifted starlight, the cosmic microwave background's faint whisper of the Big Bang. But peel back the layers, and the Amphalos Hypothesis exposes a philosophical wormhole. If the universe were designed to mimic antiquity, how could we ever tell? Imagine waking up inside a perfectly detailed virtual reality where every book in the library, every scar on your skin, even your own memories, were programmed to suggest a lifetime you never lived. Without an external reference point, the illusion would be indistinguishable from reality. This isn't just speculative fiction. The idea has roots in theological debates dating back to the 19th century, when naturalists clashed over whether Adam and Eve were created with navels belly buttons implying a birth that never happened. Fast forward to modern cosmology, and the same logic applies to light from distant supernova. If the universe were created last Thursday, complete with photons already en route to Earth, we'd have no way to prove it wasn't billions of years old. Even radioactive decay, the gold standard for dating ancient rocks, could be part of the charade. Its rates preset to mimic eons of gradual decay. But here's where it gets thorny. If the Amphalos hypothesis were true, science itself would face an existential crisis. The entire edifice of empirical knowledge relies on the consistency of natural laws over time. If those laws or the evidence they produce could be arbitrarily fabricated, the very concept of objective truth crumbles. Some philosophers counter that this makes the hypothesis unfalsifiable and therefore meaningless. After all, a theory that can't be tested or disproven falls outside the realm of science. Yet others argue it serves a vital purpose, highlighting how much we take for granted about the nature of time and evidence. The most provocative twist, quantum physics might offer a strange parallel. In certain interpretations of quantum mechanics, particles don't assume definite states until observed, a phenomenon called the measurement problem. If reality at its smallest scale is fundamentally unresolved until interaction, could the universe's past also be a kind of quantum superposition, collapsing into a coherent history only when examined? It's a wild leap, but one that underscores how deeply our perception of time might be entangled with consciousness itself. Whether the Amphalos hypothesis is a playful thought experiment or a genuine metaphysical challenge, it forces us to confront the limits of human knowledge. Every ancient tree ring, every dinosaur bone, even the light from dying stars, they could be threads in a tapestry woven with deliberate artifice, or they could be genuine relics of a vast cosmic timeline. The unsettling beauty of this idea isn't in proving it right, but in realizing how fragile our assumptions about time really are. After all, if the universe is capable of such an elaborate ruse, what other illusions might we be mistaking for truth? Imagine firing a single photon through a maze of mirrors and detectors, watching as it behaves like a particle when observed, hitting a screen in a precise dot, but morphs into a wave when unobserved, creating an interference pattern of multiple possible paths. Now, what if I told you that by tweaking an experiment after the photon has already made its decision, we can retroactively change whether it behaved as a particle or a wave? This isn't science fiction, it's the quantum eraser experiment, one of the most mind-bending demonstrations that reality, at its core, doesn't play by the rules we think it does. At the heart of this experiment lies a simple but profound setup. A photon is sent toward a beam splitter where it can take one of two paths. If we measure which path it took, the photon acts like a particle, leaving a single mark on the detector. But if we don't measure the path, the photon acts like a wave, interfering with itself to create a pattern that suggests it took both paths simultaneously. Here's where things get wild. Scientists added a quantum eraser, a device that, after the photon has already hit the detector, can erase the information about which path it took. Astonishingly, the interference pattern reappears, as if the photon's past behavior changes based on a choice made in the future. What does this mean? It suggests that at the quantum level, the past isn't fixed. The photon doesn't decide whether to be a particle or a wave until the experimenter chooses whether or not to erase the path information. This isn't just a quirk of light, it's a fundamental challenge to our understanding of time and causality. If the present can rewrite the past, then time as we know it might be more like a script that's constantly being edited, rather than a one-way street. One interpretation is that the universe doesn't settle on a single version of events until an observation forces it to. Until then, all possibilities coexist in a haze of probability, a concept called superposition. The quantum eraser experiment implies that this haze extends backward in time too. It's as if the universe hesitates to commit to a history until it knows how the story ends. Some theorists take this even further, proposing that time itself is an emergent property, a side effect of quantum interactions rather than a fundamental feature of reality. But here's the twist: this doesn't mean we can change the past in our everyday lives. The effect is confined to the quantum realm, where particles don't behave like billiard balls but more like ghostly possibilities. Yet the implications ripple outward. If time is fluid at the smallest scales, could there be larger structures, black holes, cosmic strings, or even the universe itself, where these effects become macroscopic? Could the entire cosmos be in a kind of quantum superposition, with its history only solidifying when observed by some cosmic consciousness? The quantum eraser doesn't just blur the line between past and present, it forces us to ask whether that line exists at all. Every time we peer into the quantum world, it whispers back with the same unsettling message. Reality is far stranger than we ever imagined, and the clock might not be ticking the way we think it is. Whether this is a quirk of particles or a clue to the universe's deepest nature, one thing's certain: the quantum eraser has rewritten the rules, and we're only beginning to understand what comes next. The patterns we've uncovered: galactic spirals mirroring quantum equations, particles communicating instantaneously across light years, even the eerie synchrony between quasars separated by billions of years, all point to a universe governed by mathematical precision. But what if this precision isn't just the product of natural laws? What if it's code? The simulation hypothesis proposes that our reality might not be the base layer of existence but an elaborate construct, a digital universe running on some unfathomable computer. Think of it like this: when you play a video game, the world feels real until you notice a texture glitching or an NPC repeating the same line. Could the patterns we've found be cosmic equivalents, tiny imperfections revealing the seams of our simulated reality? Consider the speed of light. It's not just a limit, it's a hard-coded constant, like the frame rate of a simulation, ensuring events render smoothly without overloading the system. Quantum mechanics, with its probabilistic quirks, could be the universe's way of processing only what's observed, a rendering optimization to save computational power. Even the Planck length, the smallest possible unit of space, might represent the pixel size of our digital cosmos. These aren't just poetic metaphors. Prominent figures like Elon Musk and philosopher Nick Bostrom argue the odds favor us living in a simulation, given the likelihood that advanced civilizations would eventually create ancestor simulations indistinguishable from reality. But here's where it gets even stranger. If the universe is a simulation, some of the 36 patterns we've explored could be intentional design choices or bugs. Take the double-slit experiment, where particles behave differently when observed. Could this be a lazy loading glitch, where the simulation only calculates a particle state when something's looking? Or the fine-tuning of physical constants, where even a slight tweak would make life impossible? Is that meticulous balance evidence of a programmer's hand, or just one of countless iterations in a multiverse of simulated trials? Then there's the holographic principle, the idea that all the information in our 3D universe might be encoded on a 2D surface. That sounds an awful lot like how modern graphics render three-dimensional worlds from flat textures. Even dark matter, which outweighs visible matter 5-to-1 but remains invisible, could be the universe's equivalent of back-end processes influencing gravity without needing to render visually. Skeptics, of course, push back. They argue that invoking a simulator is just a high-tech version of invoking gods, an untestable explanation that kicks the can down the road. But proponents counter that we might find evidence in the fabric of reality itself. some scientists have proposed looking for pixelation in high-energy cosmic rays or anomalies in the cosmic microwave background that resemble error correction codes. Others suggest that if the universe is a simulation, it might contain shortcuts or approximations in extreme conditions, like the way video games simplify physics for distant objects. Whether the simulation hypothesis is profound truth or modern mythology, it forces us to confront the uncanny elegance of the cosmos. Every mathematical symmetry, every cosmic coincidence becomes a potential clue not just about how the universe works, but what it truly is. And if we are living in a simulation, the biggest question isn't who's running it, it's why. Are we someone's experiment, a form of entertainment, or just one thread in an infinite digital tapestry woven by minds we can't begin to comprehend? The answer, if it exists, might be written in the patterns we've yet to decode, or in the glitches we've yet to notice. From the quantum to the cosmic, these 36 patterns weave a tapestry of mystery that defies everything we thought we knew about reality. They're not just curiosities, they're breadcrumbs, each one leading us toward a truth far stranger than fiction. Take dark matter's invisible web, threading through the cosmos like ghostly scaffolding, holding galaxies together with a grip we can't see or measure. Then there's the golden ratio, appearing with uncanny precision in the swirl of distant galaxies and the curl of a nautilus shell, as if math itself is the universe's native language. And what about quantum entanglement, where particles separated by light years dance in perfect, instantaneous harmony, mocking our notions of space and time? These aren't isolated oddities, they're pieces of a puzzle, one that hints at a reality where everything, from the smallest atom to the largest supercluster, is part of a grand, interwoven design. But here's the real question: what does it all mean? Are these patterns the fingerprints of a unified theory, waiting to be decoded, a single framework that could finally reconcile gravity with quantum mechanics? Or do they point to something even more radical, like a holographic universe where our three-dimensional world is just a shadow of a deeper, two-dimensional code? Some theorists argue that these mysteries are clues to a cosmos far more alive than we've dared to imagine, a place where consciousness, math, and matter are somehow entangled at the most fundamental level. Others caution that we might be seeing what we want to see, projecting order onto chaos like constellations onto random stars, yet the evidence keeps piling up. The more we study the universe, the more it seems to whisper the same message. There's a hidden architecture beneath the surface, a structure we're only beginning to glimpse. Whether it's the eerie alignment of quasars or the way black holes encode information on their event horizons, each discovery chips away at our assumptions, revealing a cosmos that's less like a machine and more like a living, breathing network. This isn't the end of the journey, it's the opening act. Every telescope pointed at the sky, every particle collider smashing atoms, every experiment probing the fabric of space-time brings us closer to unraveling these enigmas. And the most exciting part, the next breakthrough could come from anywhere. A grad student analyzing data in a lab, an amateur astronomer spotting an anomaly in their backyard telescope, or an AI stumbling on a pattern no human ever noticed. The universe isn't just hiding its secrets, it's inviting us to find them. So what do you think? Are these patterns cosmic coincidences, or the first clues to a reality far grander than we've imagined? The answer might be waiting in the next dataset, the next observation, the next bold idea. And if you're ready to keep exploring, to keep questioning, then you're already part of the adventure. After all, the greatest mysteries aren't just meant to be solved, they're meant to be shared. The cosmos is talking. Are you listening? the universe isn't just a spectacle for scientists in lab coats, it's an open invitation, a grand stage where anyone can step into the role of explorer. You don't need a billion-dollar telescope or a degree in astrophysics to start uncovering its secrets. Sometimes all it takes is looking up. Grab a pair of binoculars on a clear night, and suddenly you're not just staring at points of light, you're witnessing distant suns, galaxies spinning billions of miles away, and maybe even a meteor streaking through the atmosphere like a cosmic brushstroke. But if you're hungry to go deeper, there's never been a better time to dive in. Online platforms like Galaxies let you classify galaxies from your couch, contributing to real research that's helped astronomers map the universe's structure. Every click is a step toward discovery. Who knows, you might even spot a never-before-seen formation hiding in plain sight. For those who crave hands-on learning, local astronomy clubs offer telescope workshops and star parties where seasoned stargazers share their passion under open skies. Imagine tracking Jupiter's moons as they glide past the gas giant or catching Saturn's rings at just the right angle. It's like having front-row seats to the cosmos. And if math and physics spark your curiosity, free courses from universities like MIT or Stanford demystify everything from quantum mechanics to dark energy. The key isn't mastering every equation, it's asking questions. Why do galaxies spiral? What whispers from the Big Bang are still echoing around us? Every mystery you chase pulls you deeper into the universe's story. Then there's the thrill of the hunt. Apps like Stellarium turn your phone into a pocket planetarium, guiding you to constellations, planets, and even passing satellites. With a little patience, you could photograph the Andromeda Galaxy using just a DSLR and a tripod, a faint smudge of light that's actually a trillion stars, each one a possible sun to another world. Citizen science projects like SETI at home let you loan your computer's idle time to scan radio signals for alien civilizations. Even if you never find ET, you're part of a global effort to answer one of humanity's oldest questions: are we alone? The most exciting part, you don't have to choose between being an observer and a participant. Every time you pause to watch a sunset and wonder about the light's 8-minute journey from the sun, or ponder how atoms in your hand were forged in ancient supernovas, you're engaging with the cosmos on a profound level. The universe isn't just out there, it's in you, a living connection between stardust and curiosity. So whether you're sketching the moon's craters, joining a neutrino detection project, or simply sharing the night sky with someone who's never seen the Milky Way, remember, exploration isn't about having all the answers. It's about embracing the wonder of the questions, and who knows, the next great cosmic revelation might start with your eyes on the sky, chasing the same patterns that have captivated humanity since the first campfire stories were told under the stars. If this journey through the cosmos left you as awestruck as it did us, drop a comment below which of these 36 patterns shattered your understanding of reality. Was it the quantum particles rewriting their own past? The galaxies moving in unison toward something unseen? Or maybe the eerie precision of solar eclipses, as if the universe itself aligned the moon and sun just to show us their coronas. Every like and share helps spread these mind-bending discoveries to fellow cosmic adventurers, and hitting subscribe means you'll never miss our next deep dive into the universe's greatest mysteries. The cosmos is full of whispers waiting to be heard, so stay curious, keep questioning, and remember, the next revelation could be just one observation away. Until then, keep looking up. The universe isn't just out there, it's inviting you to play a part in unraveling its secrets.